Welcome to the AI Research Roundup. I am Alex, and today is May 11th, 2025. Alright, today we are looking at a research paper from Hugging Face's trending list, published just 4 days ago, titled Benchmarking LLMs Swarm Intelligence. This paper explores emergent coordination by LLMs, a key aspect of swarm intelligence, which is the collective behavior arising from decentralized systems. It specifically examines multi-agent systems, or MAS, which are systems where multiple intelligent agents interact, especially under strict constraints like limited local perception and communication. The authors introduced SwarmBench to evaluate LLMs in a zero-shot setting, meaning without specific pre-training for these exact tasks. So, to give us a clearer picture of what these SwarmBench tasks entail, this first figure illustrates them beautifully. The top row shows us natural examples of swarm intelligence, like cooperative wolf pursuit, firefly synchronization, and ant foraging. Then, the bottom row translates these into the abstract tasks simulated in SwarmBench's 2D grid. Here, agents, represented by colored squares, operate with only local perception, meaning they can only see a small K by K area around them, and must coordinate, sometimes with local communication, to achieve goals like reaching targets, all based on this limited information. Alright, so to get a better sense of how SwarmBench is structured, this next figure lays out its conceptual architecture. We see it is built from several interacting software modules, one handling the simulation environment, another for the LLM-powered agents, and a module defining those coordination tasks we just talked about. This modular design is really key here. It enables systematic benchmarking, detailed data logging for analysis, and makes the whole SwarmBench framework readily extensible. For example, to integrate new tasks or even an RLVR pipeline, which seems to be a system for more advanced agent refinement. Building on that architecture, this next figure gives us an overview of how different LLMs actually performed on these SwarmBench tasks. We see various LLM models along the bottom, with their scores on the vertical axis. The colored bars show mean performance on specific tasks like pursuit or flocking, with those little error bars indicating the variability in scores. It is clear that performance varies a lot, not just between models, but also how well one model does across different tasks. For instance, flocking often scores higher, while synchronization seems quite challenging for most, highlighting the difficulty of these decentralized coordination problems. Okay, so this table S1, provides the detailed numerical breakdown for what we saw visualized in the previous figure. It lists the average scores, along with standard deviations which show the spread of results for each LLM across those 5 SwarmBench tasks, plus their total scores. For instance, Gemini 2.0 Flash leads overall. The paper also analyzes emergent group dynamics using measures like action entropy, a measure of behavioral flexibility or how varied the agent's actions are, and polarization index, which gauges how much the agent's movements are aligned or coordinated, linking these dynamics to the observed scores. Following on from those scores, this next table S2, delves deeper into those emergent group dynamics. It shows significant correlations between specific dynamic features and the overall scores. We see Pearson's R values here, measuring correlation strength and direction, and p-values, showing statistical significance. For instance, a higher standard deviation of action entropy, suggesting dynamic shifts in behavioral variety, and more stay actions, indicating efficiency, positively correlate with better scores. Conversely, a high average polarization index, meaning too much rigid alignment, and a high proportion of move actions are linked to lower performance. Alright, so building on those correlations, this table S.3, presents the coefficients from a linear regression model. This model attempts to predict the overall task scores using those emergent dynamic features we have been discussing. The R-squared value here, which is about 0.245, tells us that these combined features can explain roughly 24.5% of the variation in scores. Looking at the specific features, a high average proportion of a single dominant action strongly decreases scores, while higher total action entropy, reflecting more diverse behaviors over time, tends to increase them. This reinforces the idea that behavioral flexibility is important. So to wrap things up, this research really highlights that While current LLMs show some promise in multi-agent systems, which are essentially systems where multiple intelligent agents interact, they still struggle quite a bit with complex, decentralized coordination when information is strictly local. The SwarmBench framework introduced here provides a valuable tool for measuring this, showing that behavioral flexibility is indeed crucial for better collective performance in these challenging swarm-like scenarios. Thanks for tuning in to the AI Research Roundup, and I will see you next time.